Hello there, and welcome to this collection of notebooks and tutorials on advanced digital signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, and on this notebook we'll talk about histograms, PDFs, and numerical integrations. So basically we are going to define some signals, then we'll talk about histograms and compute histograms, then we'll talk about the PDFs of the signals and calculate some PDFs, and finally we will end with some numerical integration. Let's get started. We start this revision by defining 4 signals that we are going to use to calculate histogram and to calculate PDFs. So first, I'm importing here Python libraries we are going to use. So we are going to use NumPy, we are going to use matplotlib and librosa to handle audio signals. Here we are going to use sampling frequency of 32 kilohertz, and I'm defining a time vector of 1 second that we're going to use to create our signal. So the first signal we're going to use is a sine wave with the amplitude equals to 1. So its values goes from -1 to 1, and it has a frequency of 500 hertz. We are going to use a random signal sampled from a uniform distribution from -1 to 1, also having 1 second. Then we are going to use a Laplace distribution signal, so it's a random signal sampled from a Laplace distribution with zero mean and with b equals to 1. And finally we are going to use a music signal. So this is this classic rock song from Led Zeppelin, Rock and Roll, and here I'm plotting all the signals. So we have one period of a sine wave, and I'm just plotting the equivalent time of one period of a sine wave to all the signals. So here is the uniform distribution signal, here is the Laplace distribution signal, here is the music signal, and here we can also listen. So we can listen to 1 second of a sine wave, 1 second of a random noise taken from a uniform distribution, 1 second of a random signal taken from a Laplace distribution, and 4 seconds of a music signal, because this is Led Zeppelin and it deserves more time. So we're going to use these 4 signals to calculate histograms and to revise concepts of histograms and PDF. A histogram can be defined as a representation of frequency distribution by means of rectangles whose widths represent class intervals and whose areas are proportional to the corresponding frequency. So this is a definition by the Merriam-Webster dictionary. What we mean by that is that, for example, when we look to the sine wave, so we have values from -1 to 1. We will divide these values in some intervals that we are going to call bins, and then we will count how many values are inside each bin, and this way we can build a histogram. Here I'm just defining some distributions and SymPy that we're going to use later on for the PDF. We're not going to use now, but I'm just importing the SymPy symbols function, and from SymPy statistics we're importing a uniform and Laplace. And it's very important to observe that a histogram becomes a probability distribution if we divide it by the total number of samples, such that its sum becomes 1. So this is how it looks like a histogram. So what we're doing here, we're plotting all these 4 histograms. So we're calculating here, we're using matplotlib to have the histogram, and we're using here the sine wave, the noise with from a uniform distribution, the noise from a Laplace distribution, and the musical signal. And we have here this density equals true. That means that we are dividing it by the total number of samples. So this is why we have here, for example, this is the uniform distribution signal. and its values go from -1 to 1, and we see here that the average here is 0.5. So here we have the sine wave histogram, here we have the Laplace distribution signal, and here we have the music signal. So all these histograms, they are normalized, so they are divided by the total number of samples. Yeah. So for example, if I replace here, and we have density equals to false, so we see now the sine wave is 1.4, but it goes to more or less 9. It means that there were like 9 values inside this interval from -1 to the width of this beam. So I'm using here 20 beams, so I'm dividing this range from -1 to 1, 20, so it is approximately here from -1 to 0.9, 0.8, 0.7, 0. And so on. So from 0.1 intervals we have here. Now let's go back to the density true, because we're going to use this property of histograms, normalized histograms and probability distribution later on. We've seen the histograms, and now we can move to the probability density functions. So the probability density function is a function of continuous random variable whose integral over an interval gives the probability that its value will fall within the interval. So let's see what it means by doing some examples. Once again, I'm using SymPy and importing all these functions to define symbols, define functions to calculate integrals, to simplify, having a symbolic pi, symbolic square root, lambdifies that it transforms this symbolic equation into Python and NumPy function that we can use for numerical calculation. So we have uniform distributions. When we use this density, we get PDF from a distribution. So here for the sine wave, in some previous notebook, we calculated the PDF of a sine wave, and it's given by this formula here. So here I'm defining this symbolic formula for the sine wave. Then I'm lambdifying this, so this now will be transformed into a lambda function that we can use to compute numerical values. So here I'm creating a NumPy array from -1 to 1 with steps of 0.1, and here I'm calculating this PDF, so this formula here. So I'm replacing x with values from -1 to 1 in steps of 0.1, and it plotting this, it gives this plot here, and we see that this plot here is very similar to this shape here. The difference here that it is a bar plot from a histogram, and here's a plot from this function within this range of values. So for the uniform distribution, and we assign this uniform, we defined it here, and now using this density we get this PDF. So it's a uniform distribution from -1 to 1. We have 0.5, and this is what we have also here. If we look at this histogram of a uniform distribution, we have this value of 0.5 here, and this is how the PDF of a uniform distribution looks like. For the Laplace distribution, we do the same thing. We take the Laplace distribution that was defined earlier, so here with 0 mean and the b equals to 1, and then we are having this equation here for the PDF of a Laplace distribution, and then we're plotting, and we also see that it's quite similar to the histogram of the Laplace. And the PDF of the music signal has no closed form, so there is no formula that can describe, so we have only the histogram to work with. So let's calculate the probability that a value x is inside the intervals from minus 0.4 and 0.3, and then from 0.8 to 0.9 in a sine wave. So if we go back to the definition of probability density function, so a function of continuous random variable whose integral over an interval gives the probability that its value will fall within the interval. So we want to see the probability of a value to be from in the interval minus 0.4 and minus 0.3 of inside this sine wave. So what we do is we have here now the integral. This is the PDF from minus 0.4 to minus 0.3, and then we have that it's equal to 0.034, and from the interval from 0.8 to 0.9 we calculate here and we have 0.061. If we go back to the histogram, so 0.3 and 0.4 is around here, so it's like 0.3 something, which is in fact similar to this. And if we look the histogram, oh, there's a mistake here. If we look the histogram beams, and we have, so from the interval minus, oh, there's a minus 0.4 and minus 0.3, so there's the beams 7 and 9, so it's 6 and 8, yeah. So we have here that it's 0.32, is very similar here, and from the interval from 0.8 to 0.9 we have also approximately 0.6. So we have differences here, of course, so there are two different ways of implementing two different errors, but it's very similar, and we see that in fact, yeah, there is a relation between histogram and the probability distribution, and we can take some conclusions from its relation. So this was we can do similar analysis with all the distributions, and then you compare value calculated by integrating this formula or by having here this looking inside the pin of histogram, and we see here that we are taking a value and multiplying by the width of the bin, so it's in this case 0.1, and then we take here this value and multiply by this, so it's area of a rectangle, so it's this times this, and we will find results which are similar to the integration of the PDF. Finally, we're going to talk about numeric integration. So it's the final topic of our revision. So numeric integration is the approximate computation of an integral using numerical techniques, and it exists a diverse range of different techniques. So we are going just to list some. One that is very common is the Riemann sum, that we approximate the integral by the area of small rectangles. So the integral can be seen as the area below a certain function, and if we think that this area could be approximated into many rectangles, and then we calculate the area of each rectangle, and if we add them we will have an approximation of the integral, of course with certain errors. And for this is called the Riemann sum, and we can have different ways of computing the Riemann sum depending if we start of the left. So the Riemann sum of left, so here is 0, but then it goes to the next interval, takes from the left and goes to the next interval, takes from the left and goes to the, so we see that there is an error here, an error here, an error here, and then we calculate the area of each rectangle, we add them, and we'll have the value for this integral. We can also have the midpoint, so it calculates the midpoint between two samples, takes the midpoint, and then the rectangle is drawn using this midpoint. Or we can take the right, so we take the right and goes to the left. Each one has its advantages and disadvantages and different errors. So if this is the symbolic integral of a sine from 0 to pi divided by 2, and when we compute this, a symbolic computation will give us the value is equal to 1. So now that we plot this, we just drawing to show how the algorithm works. So here we are implementing this algorithm. It's taken from the University of British Columbia. This is a very nice website, so you can take a look. There are different methods and different algorithms, not only integration, but with mathematical computations using Python. I highly recommend. But here there's a function to compute the Riemann sum, and we can choose the method midpoint, left or right. So now we are using this, so we are computing the Riemann sum from 0 to pi divided by 2. We know the theoretical value should be 1, and we have 0.991. So we see that it's a very good approximation with some errors. Another very, very important method is the trapezoidal rule. So the trapezoidal rule approximates an integral. Instead of using areas of rectangles, it's using areas of trapezoid. So we see that we have less errors using this technique. So here is the function taken from the same place to calculate the approximation of an integral using this trapezoidal rule, and we see that we get very, very good result, very close to 1, which was how we calculate symbolically. And we also can use methods from MP-Math that comes with SymPy or SciPy. They also provide methods for numerical integration. So in SciPy, what we do here, we define a lambda function. So x is equal to the sine of x, and then this is a function, and then we use this quad imported in MP-Math, so it's a SciPy, and we import this quad, and then we do from 0 to pi divided by 2, and we have also very good results. So they use different methods, different numerical techniques. And in SciPy there is also this quad from the SciPy integrate. The concept is the same. We define a function, so here's a lambda function, so x to sine of x, and we call this a quad function from 0 to pi divided by 2, and here it gives the result, and this is the error. So we've seen many different ways to calculate numerical integrals using Python, the concepts behind it. We also seen PDFs and how we can relate histograms to PDFs, and how we go from PDF to the probability of a value to be within a certain interval. So this is we had an example. You can expand this example to use the Laplace distribution, and in case we don't have a closed form for a PDF, we can, like for example the music, we can also see the probability for this piece of music, for a value to be inside an interval. And we can always do trade-offs, like dividing the range into more number of beans if it's possible. So we have beans with a smaller intervals, and that's it for this revision. So next time we are going to talk about the Lloyd Max quantizer.